Sir Ramesh sir, shall we start, sir?
Professor, ನಮಸ್ಕಾರ.
ನಮಸ್ಕಾರ ನಮಸ್ಕಾರ. ಆರಾಮಿದ್ದೀರಾ?
ಆರಾಮ. ಸ್ಟಾರ್ಟ್ ಮಾಡೋಣ.
ಸರಿ
ಸರ್ ಶುರು ಮಾಡೋಣ ಸರ್, ಇಲ್ಲ ಇನ್ನೊಂದು 2-3 ಮಿನಿಟ್ಸ್?
Good afternoon, everybody. We have with us Professor E.S. Mahesh from IISER, Pune. There will be speaking on spins as quantum workshop. And before the talk, let me give a brief introduction about his academic achievements. Professor Mahesh has done his BSc from JCBM College, Sringeri, and later pursued his MSc from Mangalore University. And after that, PhD from the prestigious Indian Institute of Science, Bangalore, under the supervision of Professor Anil Kumar. After that, he pursued postdoctoral at MIT Cambridge, MIT, USA from 2003 to 2004. Afterwards, he was awarded Humboldt postdoctoral fellowship, Germany. He pursued his postdoc from 2005 to 2007, and since 2007 he has been the faculty at IISER, Pune, and he has been awarded with many awards and fellowships. Some of them include Professor S. Subramaniam's 60th birthday lecture award by National Magnetic Resonance Society, and 2014 he was selected. He was awarded Swarna Jayanti Fellowship by the Department of Science and Technology, Government of India, and he has received grants for his research work on quantum information processing by nuclear magnetic resonance oriented spin systems as large quantum registers by Department of Science and Technology. From 2011 to 2014, he has carried out the work. And later, quantum memory based on nitrogen vacancy centers in Diamond. Again, DST Swarna Jayanti Fellowship from 2014 to 2019. He received an amount of 2,002.14 crores for this research. And later, hybrid algorithms for quantum control applications in NMR spectroscopy, MRI, and quantum computing by CSIR from 2016 to 2019 has carried out the work, for which he received a grant of 13.75 lakhs. Dr. Mahesh has published more than 10 book chapters, and he has published research papers in national and international journals of repute. More than 60 papers he has published, and his research interests include NMR spectroscopy, quantum information, quantum control and dynamics, and machine learning. With this very brief introduction, I welcome Dr. Mahesh. And also I welcome all the senior teaching faculty and students who have joined this webinar through Cisco WebEx and some YouTube platform. We have with us Dr. Girija, Dr. Vijay Lal, Dr. Pradeep, Dr. Girish, Dr. Mohsina, Dr. Zina, and Dr. Chandrakumar, and A warm welcome to all of you and all the students. With this, I request Dr. Mahesh to take over and deliver his talk. Over to you.
Okay. Thank you, sir. I hope I am audible.
Yeah.
ಕೇಳಿಸ್ತಾ ಇದೆಯಲ್ಲ? Okay. So this lecture I have prepared for students. I see that there are some seniors. If they get bored, so they can stop and ask me questions. Students are also most welcome to ask questions. I would be happy if it is interactive. I don't have to finish all the slides. It's more important to have discussions. So if there is any question, I am happy to stop and we can discuss. Okay, so I'll be talking about the spins as quantum workshop, mostly about nuclear spins, and towards the end I will talk about electronic spins. It is not a single electronic spins, as you will see. It is something called defect center electronic spins. So we will take these two systems, nuclear spins and defect center spins, and those are the platforms. And so that I call as quantum workshop. Can you see my cursor? You
Yes,
can.
sir.
Okay.
Yeah, we can see.
Okay. So I'll be using my cursor to point out. So using that, these two using these two platforms, I'll be talking about various aspects of um, uh, research that we do. For example, we can study quantum information. We can study some aspects like quantum control, quantum simulations. We can study many body effects, quantum transport. We can even study quantum foundations, and we can see how we can apply machine learning and even quantum learning, how to implement all these things using such architectures. Okay, so that is the content of this talk. It's more experimental. So far, I think you have listened to many theoretical lectures. This is going to be experimental lecture. Okay, so if you have any question or any doubt or any comments, suggestions, criticisms, please stop me and we can discuss. Okay. Okay, so as the title says, when I say it's a quantum workshop, we are going to use these systems to understand the underlying science, underlying physics of these topics, okay, from quantum information to quantum simulations, quantum foundations, and so on. So what is the underlying physics? So that's the content of today's talk. Okay. Okay, so the content is like this, outline is like this. So I will be explaining what do we mean by NMR. NMR is nuclear magnetic resonance. I'll talk a little bit about its discovery, just to tell you some story. And then I will move on to NMR spectroscopy. So that will help you understand what do we do on daily basis. Okay, when we say NMR, what do we do? And then I will also connect it to magnetic resonance imaging, which most of you are familiar as MRI. Okay, most of you know what is MRI. It's nothing but an MR spectroscopy applied in a special way, that is MRI. And then I will move on to NMR qubits, NMR quantum bits. You have already heard many lectures on qubits. Today I will be talking about NMR qubits. And then I will touch upon nitrogen vacancy center qubits. So that is the spin defect center qubits. Okay. So these are the topics. Okay. So here is the one-page summary of the entire talk. So if you understand this, so you understand much of the talk. Okay. So this is the one-page summary. So nuclear magnetic resonance spectroscopy, NMR for nuclear magnetic resonance. What do we have here is a very strong magnet. How strong? It is of the order of tens of Tesla. Okay, 10 to 20 Tesla. And you know Earth's magnetic field is 10 power minus 4 Tesla. So this is about 10 power 5 times Earth's magnetic field. It is 1 lakh times Earth's magnetic field, or 2 lakhs times Earth's magnetic field. It's very, very strong magnet. And how do we get such a strong magnetic field? By using superconducting coils. Okay. So that is maintained in a very cold temperature, liquid helium temperature, and you know liquid helium boiling point is 4.2 Kelvin. So we keep this coil in that very cold temperature and then pass current, and current flows without any dissipation. And once we close the circuit, once we close the loop, current keeps on flowing, and so then you don't need any power supply for it. So that closed loop will be passing current for about 30 years, 50 years, and that will act like a magnet. So it doesn't need any further power. It will be just needing temperature to be maintained at 4 Kelvin. Okay. So that is the superconducting magnet. It produces very, very strong magnetic field. So it is like 10 to 20 Tesla. I'll show some pictures later. So it's a very, very strong magnet. Inside the magnet, we keep the sample, and this sample can be any material. It can be like organic material, inorganic material. It can be even some other species. It can be mouse, or it can be even humans. Okay. So in MRI, a sample is us. We humans go inside, and we are the sample. In fact, NMR magnet is MRI magnet there. You have seen it in hospitals, right? So then surrounding the sample, we have coil, and this coil produces electromagnetic wave. Okay, so that is the setup here. Now let us say what this material has. So let us say it has some molecules, and molecule has atoms, and inside the atom we have nucleus, right? So inside the atom we have electrons and nucleus. So first half of the topic in this talk, we don't consider electrons. So we consider so-called diamagnetic molecules. So in which there is no net angular momentum, spin angular momentum for electrons. So we can safely ignore electrons. So we will be considering only the nucleus. Now it turns out that nucleus also acts like a tiny magnet. So it has a magnetic moment, and so we call that as nuclear spin magnetic moment, or nuclear spin. So that is a short word, nuclear spin, and it has very special property. Just like all the physical objects have some basic properties, like we have basic properties like size, mass, spatial distribution, all those things. Spin is also one degree of freedom. Okay. So it is a quantum property. It is there is no analogy in classical physics. So we call that as a spin. It's a special property of quantum system. Okay. Now, so because of the spin and because of the charge, electric charge, nucleus has a magnetic moment, and that magnetic moment interacts with the magnetic field. Just like a bar magnet interacts with the Earth's magnetic field, the nuclear spin also interacts with the external magnetic field. I said we have very strong magnetic field here. Nuclear spin interacts with that. Now, just like if you align, if you hang a bar magnet in Earth's magnetic field, it aligns in the north-south direction, right? So in the same way, the nucleus inside the molecule, inside the atom, it aligns along the magnetic field. So that is the ground state. If it is parallel to the magnetic field, it is the ground state. Now it is a quantum system. We call this as, suppose we consider a hydrogen atom. Hydrogen nucleus is proton, and proton we call it as a spin half nucleus, because spin angular momentum quantum number is half. Okay, so it is a spin half nucleus, and if you place that in a very strong magnetic field, it can have two magnetic quantum numbers, plus half and minus half. So we can say that plus half corresponds to parallel alignment, and minus half corresponds to anti-parallel alignment. And there is an energy gap, and this energy gap is proportional to the magnetic field that we apply. Okay, if there is no magnetic field, then they are the two levels have same energy. We call that as degenerate. If there is a magnetic field, then that degeneracy is lifted. That means there is an energy gap, and that is called Zeeman energy gap, because the interaction between the magnetic moment and the magnetic field is called the Zeeman interaction, and the energy gap between the parallel orientation and anti-parallel orientation is called the Zeeman energy gap. Okay, so we have one nucleus inside one atom, so the whole sample is inside the magnetic field. Then that nucleus can align parallel or anti-parallel, and accordingly it can be in the ground state or in the excited state, separated by energy gap, which is known as Zeeman energy gap, and that is proportional to the magnetic field that is applied. Okay, so now we have a system with internal energy gap, and we know the resonance phenomena. If there is an internal energy gap and we supply energy, if that energy matches with the energy gap, then there is a resonant absorption. Right? It's a very simple concept. That's the resonance. If external energy matches the energy of the internal energy gap, then there is a resonant absorption. Okay. Now it turns out that for nuclear spins, most of the nuclear spins, this energy gap happens to be in the energy of the radio waves. Radio waves, electromagnetic waves in that frequency range. What is the frequency range? It is up to about 2 gigahertz. Okay, so it can be like 500 megahertz, 1 gigahertz, 2 gigahertz. Okay, so that is the radio wave range. So in that range, if we apply electromagnetic wave, then there is a resonant absorption. If the energy of the electromagnetic wave matches with this energy gap, then there is a resonant absorption. And so we call that as a resonant radio wave pulse, radio frequency pulse, or RF pulse. So in the rest of the talk, I'll be just referring to this electromagnetic wave as RF pulse. So we are applying a pulse of electromagnetic wave whose energy exactly matches with the Zeeman energy gap. So there is a resonant absorption, and I just call that as RF pulse. Now, what's the job of this RF pulse? The job of RF pulse is to cause transitions. You know, when in the atomic transition case, so the electrons jump from one level to another level. Just like that, here, the nuclear spin can absorb the electromagnetic wave, that is the RF pulse, and it can jump from ground state to excited state. Okay, so it can cause transitions. Not only that, it can prepare the spin in a very special state. That is a very speciality of quantum physics, that it can simultaneously exist in parallel state and anti-parallel state. So what we call as superposition state. Okay, so you all know about Schrodinger cat which is dead and alive at the same time. So that is the superposition. Here also the nuclear spin simultaneously exists in two states, in some probability amplitude of the up state and some probability amplitude of down state, and that's the superposition state. Now, the good thing about NMR is that this superposition state can be very precisely controlled. You will see in the rest of the talk that this is in our control. What state you want, exactly what you want, you can prepare in NMR. Also, the second good thing is this superposition survives for a long time. Usually we say that, okay, atomic transitions, it lives for nanoseconds, picoseconds, or femtoseconds. Okay, so not more than that. But here, it can live for seconds. It can live, sometimes it can live for minutes also. Okay, so that's a good thing about NMR. So you prepare superposition, it survives for long, long time. And then not only that, so this superposition state also have this special property that they can emit particular signal, and that characterizes what is the state that is prepared. Okay. Depending on which state we prepare, the signal has all the information about the state. So I'll explain about this also. How do we get signal? We get the signal from the same coil, and we amplify, and we digitize, and we analyze. Okay, so that is the one-page summary of this whole experiment that we are going to do in the rest of the talk. Okay, okay. Now, So if you look at the periodic table, almost all the isotopes have spins. So it is not just like protons we can do NMR with. We can do NMR with almost all the isotopes, except for there are spin zero isotopes. Okay, so except them, we can do NMR with all other non-spin zero isotopes. Okay, little bit of story how it was discovered. I hope most of you have studied or you have heard about the Stern-Gerlach experiment. So what it means is that if you pass spins along an inhomogeneous magnetic field, they get separated. They get separated into two beams corresponding to up state and down state. So that is a standard Stern-Gerlach experiment, right? So that was one of the first experiments to show that there is some problem with the classical physics, and that led to the discovery of quantum physics. Okay, so that is Stern-Gerlach experiment. And what Rabi did in 1936 was that he used two Stern-Gerlach experiment back to back. So A and B both are Stern-Gerlach setups, but now they are in opposite direction. Okay, so A is in one direction, inhomogeneous field is in say up down to up, whereas B is other way, up to down. Okay, so they are in opposite direction. Now what happens? So if there is a beam which is coming from left, it is split by A and it is again combined by B. Okay, so we should get high intensity. Okay, so we should get high intensity because all the spins are again focused at the detector D. Okay, so beam is split by A and again combined by B, so we should get high intensity at detector D. What he did was, it is a very clever and ingenious setup. He put RF coil in between and he applied a homogeneous field. So that's the Zeeman effect. And then he applied the RF pulse and changed the frequency. Okay, either you can change the frequency of the RF or change the strength of the homogeneous field. He changed the strength of the homogeneous field, and he saw that at some particular field strength, okay, of this homogeneous field, the detector loses the intensity. Okay, so what is happening? So what is happening is the spins are split by the homogeneous Stern-Gerlach setup A, and then they are flipped by the RF pulse here, because there is a resonance here. Okay, exactly at some magnetic field, homogeneous field, there is a resonance. They are flipped, so up becomes down and down becomes up. And when you apply the reverse field B, they are further split. Like unlike in the absence of the RF coil, now they are further split because pins are also flipped. Okay, they are further split, and so detector doesn't get any intensity. Okay, so that is the first experimental demonstration that nucleus also has spin. Nucleus also has magnetic moment and so on. So this is the first experimental evidence, and so Rabi got Nobel Prize in 1944. Okay, so this is a very interesting experiment. You can read more about it. This Wikipedia has a very detailed story about this discovery. Okay, so now what is happening is, if you apply a radio wave, so it has electric component and magnetic component in the electromagnetic wave, and the magnetic component of the electromagnetic wave interacts with the spins, because the spins also have magnetic moment, and electromagnetic wave also has magnetic component. So there is an interaction between the magnetic component of the electromagnetic wave and the spins, and so there is a oscillation. This is also called as Rabi oscillation. Okay, so that is what is responsible for creating superposition. And so that interaction takes place exactly when the frequency of the radio wave matches with the energy gap. H bar omega of the radio wave matches with mu dot B naught. Mu dot B naught is the energy gap. Mu is the magnetic moment, and B naught is the magnetic field. So mu dot B naught is the energy gap. And when this equality happens, so then we call that as the resonance, and we call that resonance frequency as the Larmor frequency of the nucleus. And different isotopes have different Larmor frequency. Okay, so it is a property of the isotope. All right, I'll give some examples later. Okay, now we are not working with single nuclear spin. We are working with sample. As I said, there are many nuclear spins. So how many nuclear spins? It can be Avogadro number of nuclear spins, right? It can be like 10 power 15, 10 power 20, 10 power 25, and so on. So very large number of nuclear spins. Then what happens? Initially, in the absence of magnetic field, they are all aligned in a random direction. That's why you don't see that every sample is magnetic. Why? Because spins are not aligned. If spins are all aligned, 100% alignment, then you will see that every sample you touch is magnet. But that's not happened, right? In real world, that is not the case. Why? Because although the fundamental particles are magnetic, they are aligned in random direction. Okay. However, in the presence of a strong magnetic field, okay, then what happens is inside the magnet, under that 1 Tesla magnet or 10 Tesla magnets, so then what happens is the spins are either parallel or anti-parallel. As I said, the protons, if you take, they are spin half particles. They have only two levels, plus half and minus half. And so they can align only parallel to the field or anti-parallel to the field. And at room temperature, there is a paramagnetism. Okay, so that means that there is more number of spins in the ground state and slightly less in the excited state. So that's the origin of net magnetization, which is inversely proportional to temperature and directly proportional to the field. And this is the Curie's law. Okay, Madam Curie's law. And so this also is proportional to square of a constant gamma, and that is called nuclear gamma, nuclear gyromagnetic ratio. And this is about 1,000 times weaker than electronic gyromagnetic ratio. And so nuclear magnetization is million times weaker than electronic magnetization. So you don't see something is nuclear magnetic. Whenever you see magnet, it is usually electronic magnet, not nuclear magnet, because nuclear magnet is also possible in physics in principle. However, that will be million times weaker and you don't see in daily life. But because it is weak, it has a strength, and that is the long coherence time and long memory. It can store quantum memory for a long time, and that's the content of today's talk. Okay, so how can you play with that quantum memory? So here is the basic again. So you have large number of spins. One molecule is shown here, but you have Avogadro number of such molecules. And so, as I said, if you take protons, it can be aligned parallel or anti-parallel to the magnetic field. And you can call that parallel orientation as 0 bit, anti-parallel orientation as 1 bit. Okay, so now you see, so we are associating a bit of information with the state of the nuclear spin. Okay, and then since it is a quantum system, it is a qubit. So the parallel spin is now associated with the 0 state of the qubit. Anti-parallel spin is associated with the 1 state of the qubit. And now we can apply various quantum operations. You have already heard about quantum gates. We can apply all the quantum gates using these radio waves, using RF pulses. And then we can realize all types of superpositions. We can implement various quantum algorithms, and we can see the results. We can do quantum computing. Okay. So when you apply RF pulse, we can tilt the magnetization along any direction that you want. Initially, it's in Z direction. We can tilt the magnetization along about x-axis, or about 90 degree about x-axis, or 180 degree about x-axis, or 90 degree about y-axis, and any arbitrary direction. So each of these is realized by an RF pulse, okay, radio wave pulse. So we just call that as gate. Okay, so there is a quantum gate 90x pulse, quantum gate 180x pulse. That is just a NOT gate. 90y pulse is Hadamard gate. So like this. So whatever gate you want, we can just realize simply by using radio waves. Okay, so now we have a qubit, which is encoded by the state of the nuclear spin inside the magnetic field, and quantum gates, which are realized by radio wave pulses. Okay. Now about signal. How do we get signal? So you see magnetization, initially it is in the Z direction. Z direction is down to up, okay, as shown by this green arrow. So magnetic field is originally in this direction. So magnetic field is always in this direction, okay. Say that is the Z direction. And magnetization is also initially in that direction, but we can apply 90-degree pulse. So once you apply 90-degree pulse, magnetization comes to XY plane because you have rotated by 90 degrees. But now it will start precessing. As I said, there is a precession, that's a Lormer precession about the magnetic field. Now you can imagine what is going on here. It is like a magnet precessing inside a copper coil. Here is the copper coil. Okay, magnet precessing inside a copper coil. What is the effect? It's the dynamo. Just like dynamo produces EMF, here also the nuclear magnetization produces EMF, and that is called as NMR signal. And so the signal has a particular frequency that is very characteristic of the state that is prepared, the spin that is undergoing precision, and its environment, and its dynamics. Okay, so it has very valuable fingerprint information about all these things. And so that is the NMR signal. And if we can Fourier transform, so I hope students, most of the students know what is Fourier transform. It takes a time domain to frequency domain. Then we understand how many frequency components are there. If there is one frequency or if there are multiple frequency, we can see just by Fourier transform. Okay. So NMR signal is obtained by nuclear dynamo, right? Okay. Okay, now NMR spectroscopy. Okay, so you see, you take some chemical now, some compound which has many atoms, many nucleus inside, and now if you just see the signal and Fourier transform, you don't see one peak, you see large number of peaks. You may ask, I have resonated hydrogen, and all these are hydrogens only. Okay, so carbon is anyway far away in Larmor frequency, that's a different isotope. All the hydrogen is just one isotope, right? It has just one proton inside the nucleus. Now question is, why are we getting so many peaks? Okay, so I will answer that in a minute. So although these are hydrogens, they have different chemical environment, and so we get different frequencies. Now you see that depending on the chemical environment, we have resonance frequency which is different. Okay, so that's the interesting and most useful part of NMR, that we can determine uh, the we can associate each resonance peak with a particular chemical environment and figure out what exactly is there inside the chemical. Okay, and this is very useful for chemists because they want to identify the molecule whether it is this or this, and so that spectrum is very handy for them. They can immediately find out what is the chemical inside the given sample, and or if it has multiple chemicals, what are the various chemicals, what are their concentrations, what is the structure of these molecules, that also can be identified by using NMR. All this information are hidden in this. Okay, so everything is hidden in this structure and the signal pattern, and that's how the spectroscopy has been developed, and mostly due to uh, very seminal work by Richard Ernst and then he got Nobel Prize in 1991 in chemistry. So Rabi got Nobel Prize in 1944 in physics. Now it is done. NMR has got Nobel Prize in chemistry now. So now I just mentioned Fourier transform NMR. This is for those students who are still not sure what is Fourier transform. So suppose imagine you have a piano. So this is actually from an NMR book actually. So this is a cartoon. You have a piano now. You want to see how many frequencies are there in this piano. There are two ways. One way is to press each key and record its frequency. You find out what is the period of the sound that comes out and find the frequency and so on. And that's a very slow process. In fact, in the olden days, NMR was done that way. So it was done in a sequential form. You slowly change the field and record the frequency at each time. But then that is very slow process, not efficient at all. What you do here is you take a big bar and press all the keys together. Okay, press all the keys together, and it makes a horrible sound. And that is the beat pattern. It is superposition of all the frequencies. Okay, and then if you do Fourier transform, in one shot it will give all the frequencies present with all the amplitudes, respective amplitudes. Which frequency has which amplitude? Everything is there in this spectrum information, and that's the power of Fourier transform. In one shot, you get all the frequency information in a given molecule. Okay, so now we are ready to see NMR spectrometer again. So this is the below is the photograph of our lab. So we have 5 spectrometers, 4 of them are visible in this. So this corresponds to about 14 Tesla on the leftmost side, and then it is 11 Tesla, it's about 12 Tesla, and then these two are about 10 Tesla magnets. We have one more 10 Tesla magnet on this corner, which is not visible here. So these are the superconducting coils, and you see these white boxes, those are the boxes that produce radio waves and detect radio waves. Okay, so those are the NMR spectrometers. Uh, they are very powerful NMR spectrometers using which we do various experiments. And in the top, it is the schematic diagram of the magnet. So we have the cryostat here, which is holding liquid helium, and liquid nitrogen. And inside that, there is superconducting coil. And at the center, we have this yellow sample. Okay, so that's the sample which is sitting at very strong magnetic field. And then we have probe, and from the probe we get signal which is amplified and digitized, and that gives NMR signal, and then we Fourier transform and we get spectrum. Okay, so I hope now you get some picture of what is going on in our lab. Okay, so coming back to the spins, as I said, different isotopes have different Larmor frequencies. Also, if you would take same spin, I just gave example of hydrogen spins having different chemical environment. So if same spins, if they have different chemical environment, then also they have different resonance frequencies. Why is that so? So that is shown in this diagram. If you see the leftmost diagram, so there is only nucleus in the leftmost diagram. So nucleus can be up or down, and there is some energy gap. Okay, so say that has particular frequency. Let us say it has some frequency. Now you consider electron cloud. So nucleus is not bare. Inside an atom, there is always electron cloud around the nucleus, right? So there is some electron cloud. Now what is the property of the electron cloud? Electron is diamagnetic. So it shields the nucleus from the external magnetic field. So the nucleus doesn't see the full strength of the external magnetic field. The external magnetic field may be 10 Tesla, but it will feel slightly less, okay, because of the shielding caused by this electronic cloud, which is diamagnetic. And so since the local field at the site of nucleus is slightly less, the energy gap is also less. Okay, so the frequency is less. Okay, so now the peak has shifted. You see the resonance frequency will shift now because the energy gap has reduced. Suppose we have another atom, same species, another hydrogen atom. Okay, all these are hydrogen atoms. Another hydrogen atom, which is in the methyl group. Methyl group is even less electronegative. Okay, so that means electron cloud around the hydrogen is even stronger, even thicker. Okay, the electron density is even higher. So that means it can shield the external magnetic field even better. Okay, so that means the local field at the site of the nucleus is even less, and so the peak further shifts. Okay, so then now I hope you have some idea about why the same nuclear isotope in different chemical groups can have different Larmor frequencies. Okay, and that's the origin of NMR chemical shift. So depending on the chemical group, you can see that aliphatic group have one frequency, aromatic groups have another frequency. So wide range of frequencies are possible simply because of different chemical groups. Now this is very important for us because this gives addressability. So if you have a molecule and you have many hydrogens, I want to address, say, only specifically aromatic hydrogen. I just have to resonate, send a radio wave exactly at that frequency, and then it will resonate only with that, and it will not touch any other, it will not be interacting with any other hydrogen spins. Okay, it will interact only with aromatic hydrogen, that too one particular aromatic hydrogen. So that gives addressability. It is just like all of us have cell phones, but when a call comes, all the phones don't ring simultaneously, right? Uh, they are all very specific. When I get a call, you will not get a call. Why? Because that is so specific and it is addressable. It's exactly like that. So when I send a particular radio frequency, it addresses only one particular hydrogen spin. Okay. Now there is one more thing, that if we have two hydrogen spins or any other spins, any pair of spins, they interact just like two magnets interact with one another. If you hang two magnets, they try to align parallelly, right, or anti-parallel. So depending on the poles, so unlike poles attract, right, and just like that. So even nuclear spins, if they are neighboring, if they are close, they interact with one another, and that can interact with two types of interaction. One is called indirect spin-spin interaction, direct spin-spin interaction, and so on. This interaction is very important because now we are now interested in so-called control gates. So quantum gates, we need local gates like NOT gate, Hadamard gate, and so on. We also need something called C0 gates, XOR gates. And in quantum computing, without interaction, we cannot implement XOR gates. Okay, so that's very important. And so this allows us to implement universal gates. So we can apply, we can do any quantum algorithm because we have interactions, we have universal gates. Okay, so let me skip that. Okay, so now what else? So suppose we have a large molecule. Okay, so just to give an example of a big protein. Proteins, as you know, it can have thousands of atoms, right? And one can do very large molecule NMR, and you will get very large number of peaks. So it will be so crowded that they overlap with one another, and it is very hard to analyze each peak because there is so much overlapping. This is called spectral crowding. Okay, so when you have so much overlapping, what can we do? And this was a major challenge for NMR about 2-3 decades ago. People started wondering what to do with this because we have to do large protein NMR, because we want to identify the structure, we want to identify the dynamics, but then the problem is spectral crowding. So very clever methods were developed. This is called multi-dimensional NMR. So here what we do is a very special method. I don't have time to go through the details of these technical details, but here instead of one frequency axis, in earlier spectrum we had one frequency axis, but here we will have two frequency axes. For example, one for all the hydrogen spins, another for all the carbon spins. Okay, now we can see which hydrogen spin is close to which carbon spin. Okay, just by seeing these cross peaks. So cross peaks indicate which spin is close to which spin, and so that reveals the neighbors, and that is very helpful for determining the chemical structure and chemical interactions. And so multidimensional NMR was further developed by Kurt Trich, and he got Nobel Prize again in chemistry in 2002. But we can also ask this question. Suppose we have a sample all with, this is an example. Suppose we have an ice tray. Ice tray has many pits, right? So it has like 4x4 pits. And suppose that we have filled water in some of the pits, not in all. The white pits are empty, and these pink pits are filled. Okay. Suppose we want to see, and that's closed, and I don't know where water is there and which ones are empty. What can we do? So it's whole thing is closed. I can't see by eyes. But what can I do is I can apply NMR now. So if the frequency, if the magnetic field is same in all of these bits, then all of them will give same resonance frequency, right? Because as I said, resonance frequency is proportional to the magnetic field. So all of them will give same resonance frequency and they appear as one peak. Now what I am going to do is I am going to vary the field from left to right. Okay, and then I record the spectrum. Now you see the left side column has the least frequency and right side column has the most frequency and in between lesser frequency, right? So intermediate frequency. So if you see the spectrum, now spectrum depends on which pit is where and how many pits are in that column. Okay, so it is like a projection of the entire ice pit ice tray along this axis, along the x-axis. So if you take projection along x-axis, how it should look like. Okay, so that is the spectrum. Spectrum will look like that. Now you change the direction of the inhomogeneous field along y direction. Okay, so now resonance frequency will increase along y direction. Now it will ask which row has how many pits. Okay, if some row has 2 pits, you will get higher intensity. If some row has only 1 pit, you will get lower intensity. Right? So now it is like a projection along the y-axis. So now there is a method called projection reconstruction method. So once you have enough projections, you can reconstruct the entire image. And that's exactly what we do in this. It is called the projection reconstruction of humans. And this is nothing but MRI. Okay, so this is exactly what is used in hospitals for imaging our body. Okay, we can apply inhomogeneous field along any particular place, and then we can resonate the spins, and we will get exactly what is the density of spins. Mostly it is about water, because water is there in blood. So mostly it is about blood, tissues. Okay, so mostly about it's about hydrogen spins. And we see if there is no hydrogen spin, for example, on the skull layer, if there is no hydrogen spin, then it comes as black. If there is lot of hydrogen spin, say in some parts of the brain, it shows up as a bright spot. Okay, so that is it's actually finding the density of hydrogen spins having that particular Larmor frequency. And now since Larmor frequency is varying spatially, we get the image of the sample itself. In this case, it is the human head. So that's the MRI, and the first Fourier transform MRI was developed by Professor Anil Kumar, who is retired from IISER Bengaluru, and I'm very proud to be one of his students. Okay, so now magnetic resonance imaging was developed by essentially these two people. They did a lot of development, and so both of them got Nobel Prize in the year 2003, this time in medicine. Okay, so now physics over chemistry, 2 Nobel Prizes, and now it's medicine. Okay, so as you can see, the nuclear magnetic resonance is so powerful that it has wide range of applications, starting from agriculture, medicine, hospitals, functional imaging, in airport also, and food technology, materials, structural chemistry, and physics. Now coming to physics. Okay, so what we do is we take this architecture, we have the spins. Now we encode information. As I said, we say the up spin is 0 state, down spin is 1 state. But what we can do is now we can prepare superposition of these two. So that is a very characteristic property of the quantum system. This you can't prepare in classical system. You can't prepare this in bulk semiconductor transistors. You can't say that it is some probability of 0 state and some probability of 1 state, right? So these, especially these are quantum probability amplitudes. Okay, so that is the characteristic of quantum systems. Alpha and beta are complex numbers. And so we can control this superposition. We can control the values of alpha and beta. And so that's the qubit, and we can prepare any type of superpositions using radio waves. Okay. So we can have upspin or we can have downspin. We can call this as 0 or 1, or we can prepare superposition of up and down. Okay. So now what can we do with this? So I think you have already heard about quantum computing many talks. I will not repeat the theory of it. So there are many quantum algorithms. So we call them as quantum shortcuts. Okay. So quantum shortcuts means it is not that quantum computers are faster than classical computers. It is that quantum computers take entirely different routes. They take a shortcut which is not accessible, which is not possible in classical computers. Okay. If you see classical computer clock speed and quantum computer clock speed, so quantum computer may be having slower clock speed, but still it is overall it will do the job faster. Why? Because it will take a different route. It will tunnel through the problem and find the answer quickly. For example, if I ask you what are the factors of 551, and if you calculate classically in ordinary computers, it will do some algorithm called usually nowadays it is called number field sieves theory. Okay, so some algorithm, but it's an elaborate process. Okay, whereas the same thing if you do using Shor's algorithm, and this is much faster, much efficient. Okay, and it can find out what are the factors, and I will come back to this because we have done this using nuclear magnetic resonance, and we'll see what are the answers. What are the factors? So what are the factors of 551? Now, so back in 2000, so De Vincenzo, he said there should be some criteria for quantum computing. So there should be scalability. So that means we can increase the size of qubits as many as you want. And then it should be possible to bring all the qubits to ground state, and that's called initialization. All the qubits should have long memory, and there should be good universal control, which means there should be universal quantum gates, and there should be efficient readout, qubit specific measurement. So these are the various criteria for quantum computing. And NMR, although it is a very nice testbed, there are some challenges which are still yet to be solved. So that's a challenge for us, and many people are working on it. And one of the important challenges about scalability that comes because of some of the issues in the initialization. So I'll come back to this because we have nuclear spins, as I said, is they provide million times lesser magnetization than electronic spins. And that gives challenges in terms of producing so-called pure quantum states. And so that's a challenge. And we are many of us are working on it. And it also needs to be more sensitive. Okay. And in the next topic, that is the nitrogen vacancy centers, I will address some of those. Okay. Okay, so let me just summarize. So we have many nuclear spins, and we assign bits to the state of the nuclear spins. And so we have a quantum space. It is called Hilbert space. So that encodes all the states, superposition states that is possible. We can take the spins from any initial state to any final state, and that is the job of quantum control. And finally, we can make measurements. Okay, and we can have number of qubits. So we can take many molecules depending on which how many number of qubits that we want, whether we want 2 qubit, 3 qubit, or so on. All right, so this is an example for 12 qubits, another 12 qubit system. This is 38 qubit system. And when I show this kind of picture, this means these rectangles, they correspond to radio wave pulses. Okay, and this connecting bar, so that indicates the spin-spin interactions. And as I said, they are very important to realize the C0 gates, XOR gates. Okay, so this is how we can realize C0 gate, and using those gates we can factor. So this is one example. So we factored 551. That's the question I gave you a while ago. Using these three spins, 19F, 13C, and 1H, and we found that at the end of the algorithm, we used one particular algorithm called adiabatic algorithm. At the end of the algorithm, we found there is higher population in these two states, 0, 1, 1 and 1, 0, 0. And if you convert that back to decimals, okay, so 1, 0, 1, 1, 1, and then 1, 1, 0, 0, 1. So it comes to 19 and 29. And if you multiply, you get 551. So these are the factors determined experimentally using nuclear magnetic resonance. Okay. Okay, so that's one example. You can do quantum computing using nuclear spins, and this is another example. So where you can control large number of spins and we can entangle. So that's a very special state, and we can study physics of entanglement and so on. And we can realize large number of qubits. So for example, these are the 12 qubit system, 18 qubit system. Recently, we have shown 38 qubits and so on. One can go for even larger spins. For example, in solid state NMR, so we take the spins in a crystallite. There, people have shown up to 4,899 spins. Okay, so 4,899 qubits. Okay, and they studied relaxation effects. So this is not a quantum algorithm, but they showed what is the lifetime of quantum superposition in such a very large state. Okay, what can we do with this? What next? So we can what we are working on is something called hybrid quantum computing. That means we have a quantum core and surrounded with a classical network. We can do something called quantum reservoir computing, and currently we are working on it. And if that is successful, then we can do certain aspects faster than simply using classical network. We can use quantum core, and this hybrid is more powerful than either of them. Okay, so that's the goal. So that's the project that is going on. Okay, so one important aspect I wanted to say, that is the quantum purity. Just now I mentioned that nuclear spins have very less energy gap, and so they have lesser polarization or magnetization. One way to increase magnetization is to transfer magnetization from other systems. For example, if you shine light, uh, atomic spins can be highly polarized, and you transfer that to electrons. And electrons get highly polarized, and you transfer that to nucleus. Okay, so this kind of transferring polarization is called hyperpolarization. Okay, so using that you can realize very high purity. That is one way to address challenges in nuclear magnetic resonance. And one example of how hyperpolarization works is in this particular system. This works very beautifully. So this is another architecture that I was mentioning. This is called nitrogen vacancy center in diamond. So basically it's a diamond. Diamond is a carbon lattice, as you know. And here one carbon is replaced by nitrogen, and other carbon, neighboring carbon, is just removed, and so there is a vacancy. So that's why it is called NV center, nitrogen vacancy center. Okay, so one carbon is replaced by nitrogen, another is vacancy. And this has okay, there are various ways of making NV center diamond. So this is one way. So you can make a diamond using CVD growth, and then irradiate with some helium particles, and then give heat treatment, and then you get NV centers. And they look pink, and sometimes they are also called as pink diamonds. And pink diamonds are usually NV center diamonds. Okay, so now you use a confocal microscope and a detector, and this is the lab in our institute. So we have a confocal microscope here and a detector. We detect the fluorescence which comes out of the NV center. And what is the principle? The principle is as follows. At room temperature, if you see what is the energy level diagram for NV center, it has 4 important levels. Okay, so there is a ground state corresponding to m is equal to 0. So that's the spin quantum number. And there is slightly excited state corresponding to m is equal to plus or minus 1. This whole thing is in the electronic ground state. And similarly, for the electronic excited states, there are again m is equal to 0 state and m is equal to plus or minus 1 state. So there are 4 levels. Okay, now if you shine green laser, okay, so then what will happen is the electrons get excited from ground state to excited state, G to E. But when they come back, okay, when they de-excite, they do that preferentially for this level at the expense of other levels. Okay. So from all other levels, they come to ms equal to 0 state. So that is a very asymmetric de-excitation, very specific de-excitation. That is a property of this particular system, NV center. And that has two aspects, two effects. One is you get very highly polarized because all the spins are now in that particular state, ms equal to 0. That means it has very strong spin polarization. Secondly, this gives very strong fluorescence. Okay, so that this process gives very strong fluorescence, and so it is useful for both preparation as well as detection. And so using this nitrogen vacancy center, people have shown up to 10 qubits. Okay, so we can have central NV center, which can give you 2 qubits, and then surrounding carbon-13 spins, nuclear spins, that can give remaining spins. So we can get up to 10 qubit solid state NV center register, and that has a quantum memory of about 1 minute. So that's a really exciting thing. And so this is a while ago. This is about 5 years ago, and already there are tremendous progress in this. So some of the advantages of such systems is you get very strong polarization. As I said, it is hyperpolarization because you are optically polarizing the spins, and you are shining green laser, and you are getting fluorescence, pink fluorescence. And they have fairly good quantum memory and fairly high quantum control. You can get high fidelity gates. Measurement is very sensitive because of this preferential fluorescence from the 0 state. 0 state gives fluorescence, and which is excessive compared to 1 state. So you get preferential fluorescence from the 0 state. So that is the measurement, and it is ease of experimental setup. Okay, so that is you don't need vacuum, or you don't need cryogenic temperatures. Everything works under ambient conditions, and so that's a big advantage of nitrogen vacancy centers, right? You can also realize NV centers on chip, and you can fabricate it, and you can miniaturize it, and so on. Okay, so that's the summary. Okay, so that's the end of the talk. So I think I have taken 5 minutes more. Let me summarize. So we have used the spins, essentially nuclear spins and electronic spins of NV centers for various aspects. So first, I described NMR spectroscopy, and so I described a little bit of quantum computing with few examples, how we can realize gates, how we can realize some algorithms, how we can read the results, and so on. And so I just want to impress you that we can do all these things. We can do quantum control developments, which means we can do research on building efficient gates. We can do research on quantum simulations. We can study physics of many bodies, many particles, and quantum transport, quantum foundations. For example, in this particular experiment, we have studied wave particle duality. So how sometimes we get wave nature and how we get particle nature, we studied in this experiment. And so we can bring in other technologies, other concepts like machine learning, and so on. So NMR provides a test bed for studying various things, and that's why we call this as quantum workshop. Thank you.
Thank you very much, sir. There are few questions I would like to ask here in the chat box, sir.
Yes, yes.
In quantum technology applications, NMR platform is considered to be ensemble systems.
Correct.
Will you please illuminate the audience about such comments?
Yeah, so as I said, so the signal comes from Avogadro number of spins, right? And so you don't work with single spin. Whereas in the case of NV center, you are using confocal microscope. You can focus the confocal microscope to one nitrogen vacancy center and get signal only from that. Okay, so that is a non-ensemble technique because you are looking at one at a time. Whereas, but there is one thing, you are doing time ensemble because you can't, normally you don't detect a single photons coming out from NV center, you do time averaging, that's called time ensemble. But in NMR, what we do is called space ensemble. That means you collect signal from all the spins in that sample and then take an average. Most of the time in quantum computing as well as in studying quantum physics, you read expectation values, okay, not the eigenvalues. As you know, expectation values already has the way of getting expectation value is take the eigenvalue and do ensemble average. Then you get expectation value, right? So ensemble average is already there in the theory of expectation value. And for getting expectation value, NMR is ideal because you already have an ensemble and signal is already taking expectation value. Okay.
Thank you very much, sir. Any other questions? I request audience to raise their virtual hand so that I can unmute them. If no questions, meanwhile, we can take some. Yes, ma'am. Yes, ma'am.
Yeah.
Ma'am.
Thank you, Dr. Mahesh, for a wonderful lecture. In fact, many of the students, teachers here might have got benefited from it. And I'm sure most of them will look into the YouTube video and ask their students also. In fact, I am also benefited from it. I'll ask my students to go through the video lecture and learn. Like continuing on what Usha asked, that ensemble kind of a does that affect the status of NMR computing in comparison with that of other superconducting photonic qubits and such other quantum processors? I hope I'm clear in my question.
Right. So for quantum computing, it is not that much of a problem because at the end you are doing an ensemble average because you are extracting expectation value. For quantum communication, you don't want ensemble average, right? Communication, you want to send one message at a time and just you want to see what is the result. Anyway, quantum communication is not the ball game of NMR because it is a localized setup, right? So for quantum computation, that is ensemble is not an issue. Issue is the polarization. If you can do hyperpolarization and get high quantum purity, that's it. Then there is no issue.
Okay. So quantum communication, like people like in the NQM present quantum mission. So the importance given to NMR quantum, like the funds allocated, etc., etc. Can you just comment on it?
So as I said, I don't look that way. I just look what is the ideal architecture for a given task. For example, communication NV center is the ideal because you can get. So, for example, it is used for quantum amplification. You have communication network, which I think if you use optical fiber, it can go only up to 30 kilometers, and then you have to amplify. And there, indeed, there is a proposal to use NV centers to amplify that signal. Quantum information can be amplified, and then again send it. That is the way their NV center is useful. Basically, so what we can look is which spin is ideal for which task.
Okay. Yeah. Thank you.
Thank you very much, sir.
Yeah.
Sir, there is one more question. How entanglement is happening in NMR qubit?
How entanglement?
Yes, sir.
Yeah. So as I said, the spins, if they are close, they interact with one another. right? So there is a spin-spin interaction, just like two bar magnets interact, spins also interact. When during that interaction, their state gets entangled. Okay, so they get entangled, and that entanglement can be very precisely controlled by using radio waves.
Thank you very much, sir.
Yeah.
Over to you, sir.
Thank you very much, Dr. Mahesh, for a very, very scholarly and insightful talk.
Are there more questions from students?
Yeah,
Are there students who?
students are there. Dr. Girija, students ಏನಾದ್ರು question ಕೇಳ್ತಾ ಇದಾರೆ ಅಂತ ಸರ್. Okay, in the meantime, I thank you immensely for your time in making this presentation very lively. And this nuclear spins as quantum workshop was very, very useful for students and young faculty. We have with us very senior Professor K.S. Mahesh sir. Sir, for your comments. Mahesh sir.
It seems he joined a bit late ಅಂತ ಅನ್ಸುತ್ತೆ. ಈಗ ಕೊನೆಗೆ ಜಾಯ್ನ್ ಆದ್ರು ಅಂತ ನೋಡಿರ್ಲಿಲ್ಲ ಅವ್ರ ಇದನ್ನ.
Now Dr. Srinath sir is there from IISER. So Srinath.
Sir, good evening, sir. It was quite a fantastic talk. Congratulations to Mahesh. A lot of new things, maybe students. I too have learned RF pulse-based gate generation, signal-based like Fourier transform and its application in NMR and identifying interaction of hydrocarbons, thereby creating a spin concept and creation of the gates. I mean, these are all the few new things which maybe students will appreciate that and they will try to learn more in that direction. Also magnetic based NMR, I mean, we are very happy that he has shown some of the photographs from his laboratory, and he has nicely covered mutually exclusive topics compared to previous all our quantum technology talks, and very useful, and thank you, Mahesh.
Thank you. Thank you.
Dr. Usha madam.
She's traveling.
Oh, I see. Okay.
ಅದಕ್ಕೆ ಚಾಟ್ ಬಾಕ್ಸ್ ನಲ್ಲಿ ಪ್ರಶ್ನೆ ಕೇಳ್ಬಿಟ್ಟು.
Thanks, Dr. Sudha madam and all the senior faculty for joining this webinar. Dr. Girija, Dr. Girish.
Ramesh sir, just an interruption. Just there was a document released by the government of India called Mega Science Vision, where again they have insisted on quantum technology. I just draw the attention of all here to have a look at that document.
Thank you. Thank you. Yeah.
Mohsin, Dr. Zina, Dr. Chandra Kumar, Dr. Madan. For all of you, thank you. Large number of students have joined from BLDE. We are sitting in classroom and watching this webinar. For all of you, thank you very much. This 5 days webinar series has been very successful. We have seen students joining both on DiscoWebEx and YouTube platform. For all of them, it will be very useful, and they will have a lot of take-home message from Dr. Mahesh sir's presentation. If you support us like this, we would like to have many more talks like from experts like Dr. Mahesh, Dr. Sudha madam in future as well. Once again, thank you for joining us for both first series of talks and the second series of talks and making it a success. Mahesh sir, thank you very much once again.
Thank you.
Thank you. Thank you.
There are 2 questions in the chat box.
Yeah,
the number of qubit in NMR quantum computer in IISER Pune.
So as I said, it depends on the structure that of the molecule. So recently we have published 38 qubits, and we are also working on 50 qubit register. In solid state NMR, so we don't have individual control, but their qubit number is large. I showed one German paper where they have shown the decoherence study. They are studying physics of large number of qubits. They studied the physics of 5,000 qubits. So it is their goal is to study the quantum memory in such large number of qubits. When you put such large number of qubits, what is the lifetime of quantum memory? So for that, we can have hundreds of qubits, even thousands. Okay, so that's the thing. Now, question is for which task, which register is best? Hmm. So, yeah, we have shown up to 38 for some task, and yeah, hundreds of qubits can be realized for some other tasks.
Thank you very much, sir. And how many qubits are entangled, sir?
When I say this 38 qubits, they are all entangled. Yeah. And so in solid state also there can be larger number of entanglement, but there the goal is not algorithms. Goal is to study physics of quantum memory.
Thank you very much, sir.
Nivita,
Yes,
Umesh,
yes, sir. Yes, sir. Yes, sir. Yes, Mahesh sir ಮಾತಾಡ್ತಾರೆ ನೋಡಿ sir.
Dr. Mahesh sir. Hello.
think connectivity issue ಇರಬಹುದು.
ಈ ಕನೆಕ್ಟಿವಿಟಿ ಇಶ್ಯೂ ಇರಬೇಕು ಅನ್ಸುತ್ತೆ.
Yes, yes.
I also thank Mr. Gururaj and Dr. Anand Raman for posing so many questions. These questions will be very useful for students also to understand better. Thank you very much. Thank you, Mahesh sir.
Thank you. Thank you. Bye.
Sudha madam, thank you very much.
Yeah.
Aksha madam,
Yes.
thank you. Dr. Mahesh sir, thank you. For all of you, thank you.
Dear sir, I'm sorry. There is lot of disturbance near me. So, that is one reason I could not concentrate. Are you able to hear me, sir?
Yes, sir, please continue. Ready, sir, ಕೇಳಿಸ್ತಾ ಇದೆ.
ತುಂಬಾ ತುಂಬಾ ನಾಯ್ಸ್ ಇದೆ ಇಲ್ಲಿ ನಮ್ಮ ಮನೆ ಹತ್ರ. ಹಾಗಾಗಿ
ಮಾತಾಡಿ.
I had heard about Dr. Mahesh. Today I could see his wonderful presentation. Every picture, I think, started telling really the factual information. I enjoyed listening to the lectures and how this NMR helps in quantum computing. Thank you. Maybe you had called me earlier. Because of the noise, I could not listen to you. Thank you so much, sir. Thank you for the opportunity.
Thank you, sir. Thank you, sir.
Thank you very much. So, thank you everybody for joining this webinar series. We'll plan one more webinar series and also offline workshop. Whoever is interested can join offline. We'll try to contact experts, and depending on their convenience, we'll organize an offline workshop at PST. Maybe next month or in December. Thank you very much.
Thank you very much, sir. Thank you very much to all the students and teachers. And we have sent you the feedback form link in the chat box. Please submit it based on your attendance and feedback form. The certificate will be emailed to you. Thank you. Thank you very much.